In this video, we are going to go over a problem and how to solve it. The directions say write out the solution, including all 4 steps listed here. Step 1 says state the hypotheses HO and HA, so that's the null hypothesis and the alternative hypothesis. Step 2, calculate the appropriate test statistic showing your work. At minimum, write the letter of the test statistic, the formula, the numbers filled into the formula, and the final answer. Round to 2 decimal places. Step 3 says decide whether or not to reject the null hypothesis, which is HO. And then it says state what happened to HA, which is the alternative hypothesis. For this step, show both the p-value approach and the critical value approach. Step 4 says interpret the hypothesis test in terms of the original question. Be sure to reference the significance level in your interpretation. Answer the question, is there evidence that the customers at these new locations are waiting longer than the maximum mean time dictated by the retailer? Should action be taken based on the results? So these 4 steps in the directions align with the 4 steps of hypothesis tests as we are learning them in class. So let's see what this one is about. A chain retailer has target service levels that each location is expected to deliver. The target established for customer wait times at checkout is 210 seconds or less. The retailer opened a new location called store number 140. An analyst was tasked with testing wait times at the new store. Any store found in violation of the 210 seconds or less standard must take action to reduce waiting times. The analyst took a random sample of 34 customers at store 140 and measured the time they had to wait to check out. In the sample of customers, the mean waiting time was 245 seconds. Drawing on past experience with checkout times at this retailer, the analyst assumed a population standard deviation of 86 seconds. Perform and interpret a hypothesis test to determine whether the population mean waiting time at store 140 is longer than 210 seconds at the alpha equals 0.05 significance level. Is there evidence here that store 140 needs to take action to reduce waiting times? When approaching a hypothesis test, the first question that should be on your mind is what is the parameter that they are testing and what do they want to know about that parameter? So a parameter is always a characteristic of a population. So a population variance, a population mean, a population proportion. Those are all examples of population parameters. And every hypothesis test is going to be about some type of parameter. In the 3rd paragraph, it says perform and interpret a hypothesis test to determine whether the population mean waiting time at store number 140 is longer than 210 seconds at the alpha equals 0.05 significance level. So their question is about a population mean. It happens to be the population mean waiting time in this case, but it's a population mean. So it's a parameter of a population mean. And their question about it is it longer than 210 seconds? The fact that their question is a population mean higher or greater than, or in this case longer than 210, which is a given number, that sends you to a hypothesis test for a single population mean. Because that particular hypothesis test can answer that type of question. Now, let's talk about what formulation of this test we're going to use. Are we going to use an upper tail, a lower tail, or a 2-tailed test? And that's based on the actual specific question that they're asking. So in this problem, you have a chain retailer that has a target service level. They want all the stores in the chain to have checkout times that are 210 seconds or less. So any store that has average checkout times 210 seconds or less is fine. They are meeting the standard. Violation of this standard would be checkout times that are longer, right? Because longer is worse when it comes to checkout times. So what they're looking for is stores that have checkout times longer than 210 seconds because those stores would be violating the standard and those exact stores would need to take action to reduce their waiting times. Given that the question they have is the population mean longer than 210 seconds, which aligns with is the population mean greater than a given number, 210, we will use an upper tail test in this case. So we're going to use upper tail hypotheses in solving this particular problem. Now, taking a look at our pair of hypotheses, we have HO, which is the symbol for the null hypothesis, is mu, which is the population mean that we're testing, is less than or equal to mu 0. Mu 0 is the given number. The alternative hypothesis, HA, says mu, which is the population mean waiting time, is greater than mu 0, which is this given number. So we have to identify mu 0. Mu 0 in this problem is 210. So anywhere you see the symbol mu 0, the notation mu 0 in any of the formulas, substitute in the value 210. So at this point, we can actually formulate these hypotheses, meaning write them down. The null hypothesis in this case is mu is less than or equal to 210, and HA is that mu is greater than 210. So the formulas have mu 0 on the right-hand side, but when we actually apply them in a hypothesis test, we fill in the mu 0 that applies to this particular problem. In this case, they want to know if that population mean is greater than 210. Okay, now we are on to step 2, and step 2 is choose and calculate a test statistic. Now, from our references, it says choice 1, if the population standard deviation sigma is given, calculate z-test. And z-test has the formula given here. Choice 2 says if the population standard deviation is not given, using a sample standard deviation instead, calculate t-test. Okay, so that is how we choose. So looking at this problem, where is the standard deviation information? Aha, I see that the last sentence of the second paragraph says a population standard deviation. The analyst assumed a population standard deviation of 86 seconds. So that 86 seconds is a value of sigma. What does that mean in terms of our choices? Well, population standard deviation was given. So we call that sigma is known, because sigma is a notation that means population standard deviation. It's known to be 86 seconds in this problem. So sigma equals 86. Sigma is known, so use z-test. To calculate z-test, we need to identify 4 numbers, 2 of which we've already identified. Mu 0 is the hypothetical value of the population mean, which is 210. Sigma, which is the population standard deviation, is 86. We also need to get n and x bar. So x bar is the sample mean, and we see that the mean waiting time in this sample of customers was 245 seconds. So x bar is 245. The sample size is always the number of members of your population that have been selected into the sample. So here we had a random sample of 34 customers. Each customer has a wait time in line. Average wait time for the sample was 245 seconds, and that was measured on these 34 customers. So 34 is n, sample size. The directions said, calculate the appropriate test statistic showing your work. At minimum, write the letter of the test statistic, so that's z-test. The formula is x bar minus mu 0 divided by sigma over the square root of n. The numbers filled into the formula, and the final answer rounded to 2 decimals. So x bar is 245, mu 0 is 210, divided by sigma, which is 86, divided by the square root of n, which is 34. We can calculate this in Excel in one step by using parentheses around the top and the bottom of the fraction. In Excel, this would be equal sign, open parentheses, 245 minus 210, close parentheses. So that forces the subtraction on top of the test statistic to be done before this division, so division sign, and then we also have to separate out the denominator so it gets calculated separately. Open parentheses, 86 divided by SQRT is the function in Excel, open parentheses, 34, close parentheses, close parentheses. Hit enter, and you get 2.37306. Rounded to 2 decimals, that is going to be 2.37. And there we have our z-test statistic. Having completed step 1 and step 2, we now turn to step 3. So I've changed my references on the left-hand side. Step 3 is where we decide whether or not to reject the null hypothesis. For this step, we need some key pieces of information. First, what is the alpha significance level? In this problem, alpha is 0.05. We need that for the p-value rejection rule and to look up the critical value. Second, we need to decide on the distribution to use, and that comes from the letter of the test statistic. So in this case, we will be using the z distribution for the z-test statistic. Finally, we need to know what type of test this is because that determines the rules to follow when we get to the rejection. This is an upper tail test because we set up upper tail hypotheses. So we will be using upper tail rejection rules. And we'll start with the p-value approach. For the p-value approach to rejecting the null in an upper tail test, these are the rejection rules. So the first thing we need to do is look up the upper tail p-value of the test statistic. Statistic is 2.37. Upper tail p-values for z-test statistics are found on the z table. 2.37 to the first decimal place is 2.3, to the second decimal place is 0.07, and where those two meets, we get the upper tail p-value of 0.0089. So the upper tail p-value is 0.0089, and the rule says if the upper tail p-value is less than or equal to the alpha significance level, reject HO and accept HA. And that is exactly what is going on here. 0.0089 is less than 0.05, so we will reject HO and accept HA. If our p-value had been greater than alpha, we would be in the otherwise condition and we would not be able to reject HO. But in this case, we can reject HO because our p-value is less than alpha. Let's turn to the critical value approach. We have a different set of rules. First step says look up the upper tail critical value for this alpha significance level. So the upper tail critical value of z at alpha equals 0.05 is something that you're going to find on the z table in the critical value inset in the upper right hand corner. So our alpha is 0.05, which means our z critical value is 1.645. Since this is an upper tail test, we just leave it positive because upper tail critical values of z are positive, being in the upper tail. Let's do the rejection diagram and then see how it comports with the rules. So our rejection diagram has the z distribution and a rejection region that has a boundary of the critical value. So the critical value 1.645 is actually the lowest your test statistic could be, and you would still be able to reject the null. So the rejection region is any z to the right of 1.645, which is any z test statistic that is higher than 1.645. The total area in that upper tail is 0.05, and that is set by alpha. So we're looking for a test statistic that's less likely than alpha. 2.37 is in the rejection region. It is far out in the upper tail, past 1.645, and so it satisfies the rejection rule. 2.37 is greater than 1.645, so reject HO and accept HA. So you can either have the diagram with the critical value and the test statistic marked, or you could just have this statement, 2.37 is greater than 1.645, so reject HO and accept HA. So before we move off of this, though, I want to explain a little more about the connection between critical value approach and p-value approach, because this entire purple shaded area to the right of 1.645 is 0.05. The upper tail p-value of 2.37 is actually this pink shaded area to the right of 2.37, right? That's the upper tail p-value if we drew it in. And we actually know the value of that p-value. It is 0.0089. So by the p-value approach, we compare the p-value directly to alpha, but by the critical value approach, we instead compare the test statistic to the critical value. But it all ends up in the same place. Is the p-value less than alpha? And we set up our rejection region in order to determine that. So now let's turn to the last step, which is the interpretation step. The tail test for a single population mean, when the null is rejected, has the following interpretation. At the alpha significance level, we can conclude that mu is greater than mu0. And here's why. It comes from the alternative hypothesis. So the alternative hypothesis was mu is greater than 210. That mu is the population mean we are studying in this problem, which is the population mean waiting time of the customers at this particular store. Greater than, I'm going to say longer than in this case because we're talking about time. And 210 seconds, well, that was what the retailer, the chain retailer, set as their target maximum in terms of waiting times for the customers. So this was set by the retailer. In this test, this alternative hypothesis was accepted. And in statistics, accepted means proven true at this particular significance level. So that's where the interpretation comes from. At the alpha equals 0.05 significance level, we can conclude that mu, which is the population mean waiting time at store 140, is longer than the target maximum that was set by the retailer. So this store has higher average wait times than dictated by this policy maximum of 210 seconds set by the retailer. So it needs to take action to reduce its wait times to bring it below the target. And that is the solution to this problem.